in Chapter 6, Mechanical Behavior. And we're going to look today at some additional elastic constants still in the elastic region of space. Okay. So let me go ahead and first correct this slide. This should say sigma. Font got messed up here and called it S. So again, we're going to have a sample that we've pulled on. We're originally at L0, and we stretch it to L here in a tension test. Okay, so we know that we can define our strain in the direction of pull. We're going to now be more specific and call that the Z direction. So that axial strain is then again just this change in length over the original length, right? But when we do that, the sample doesn't maintain the same volume. Most of the time, the volume of the sample overall will increase somewhat as we're stretching bonds. But at the same time that we're stretching in one dimension, the sample will typically shrink in the other dimensions, right? So if this was a rod, then it would be shrinking in the radial direction. All right, so we can also talk about a delta L or a delta W here, if you want to call it width. So we can take, again, the final width minus the original width over the original width. So you can see it's the same definition. It's just now that this lateral strain is going to end up a negative quantity if we're pulling in tension. If we're pushing compression, then it would grow and we'd end up with a positive lateral strain. Okay, so this is my axial strain in the direction of pull, and this is my lateral strain in the lateral directions. And if we take the lateral strain value and divide that by the axial strain value, and then we're going to put a negative sign out here, that's going to cancel with the negative signs in these lateral strains so that we have a positive quantity. This is referred to as the Poisson's ratio. And this symbol here is not a V, but it's actually the Greek letter nu. So that's our Poisson's ratio. So here's a chart of the values for the Poisson's ratio. As if in condensia again of the sample, you can see again they cluster into different classes of materials. But take a look at the range of the Poisson's ratio. You can see that it seems to have a limit at about 0.5, right? And we do have some materials dropping off here below 0.1, but really most of them seem to be, somewhere in this sort of 0.2 to 0.5 region. We could roughly say that the metals are somewhere at about 0.33 or a third. You can see the elastomers are very close to the 0.5 value, polymers around 0.4. So what's the significance of these values? This 0.5 value is the case for an incompressible solid. Okay, so this is where the change in volume is essentially 0. All right, so ideally right at 0.5, the amount that you stretch the sample in the one dimension will get countered by the amount that it's contracting laterally so that the overall volume of the sample does not change. Okay, so a lot of biomaterials fall into this category and our elastomers do. And then as we get below that value, the volume is increasing. So as we move this way, delta V change in volume is greater than 0. Okay, so we're not quite contracting as much as we are stretching. But you can see from this chart, this idea that metals are about a third is not great, but you will see in almost all textbooks, if we don't have a number for a metal or an alloy, and we just want a quick calculation, that people use a third all the time. We can see for the polymers, though, the convention would be to use 0.4. And then if we go ahead and take a look now at the shear modulus, the Young's modulus, and the Poisson ratio, you can see that they're not independent of each other. If I know any two, then I can get the third. Okay. So again, this is for linear elastic behavior for isotropic materials. So this particular equation doesn't take into account an anisotropy that might come if we were looking at a single crystal. All right, sorry about this note. We're not using the CES software this summer. So here's the value of the shear moduli. You'll see that they're not much different than the elastic moduli. You can see that from this equation. Let's say that nu was something like a third, right? Then this would be E over something like 2.6. And so we expect the shear moduli to be a factor of 2 or 3 different from the elastic modulus, but not orders of magnitude different. And so they're fairly similar. Again, the materials group very nicely when we plot this versus density.